I welcome you all to this explanation video in which I am going to explain you how to solve the question about the satellite that was hovering above the Earth. My name is Max, and here we go. At the left top corner I've drawn the Sun with a radius 1, for the Sun was number 1, and we have the satellite, and there the temperature is T2, the Sun is T1. Now this question was about visibility factors, and to understand this we have to make quite a detailed sketch. So we also have a distance between the Sun and the satellite, which I'll call S, between Sun and satellite. And also now we have to conclude that the Sun is radiating in all different directions. So therefore we have to take a visibility factor into account. And we have a visibility factor f1 to 2 and f2 to 1. So the visibility factor is a fraction of the radiation a object sends out and also reaches the other object. So also, let me take another color. The satellite is sending out radiation to the Sun. And what we're going to do is say that all the radiation from the satellite is reaching the Sun, and therefore this fraction is 1. Because the Sun is way bigger than the satellite, this is true. And also, since the radiation from the satellite is so much lower than the Sun, it actually does not really have a big influence on the temperature of the Sun. But the radiation that reaches the satellite from the Sun is of course way smaller because it's going in all sort of directions. But how to calculate this? Well, for this we have a formula, which is the area of the object that is reached. Oh wait, I made a small mistake here. So actually this one is 1 and this one is the area of 2 over A1 star. So what is A1 star? That is a new diameter of the Sun, and the area it is over n. So this is the new area over which the radiation will spread out. And because the distance between the Sun and the satellite is so large, it will have a really low value. So let me see, A2 will still be A2. We know this number from the exercise. And this new radius, so the radius, let me take a red here, from the center of the Sun to the outer center of the radiation circle, is 4 pi times r star squared. And this r star now is our radius from the Sun plus the distance between the Sun and the satellite, as you can see from the sketch. So then also r star squared equal to this squared. And now you should notice that from the numbers that were given in the exercise, that r1 is actually way smaller than the distance between the Sun and the satellite. And therefore r star squared is about equal to distance between the Sun and the satellite squared. So now we got our visibility factors. Now we just have to set up a internal energy balance and see that it is equal to the incoming radiation, and this f1 to f2 net. And we also have said that this satellite was isolated. So no heat flow is going to that side, and therefore you have no other terms in this equation. We can set this one to 0 since we have a steady state, which of course is not true, but for the ease of calculation we have assumed this for now to see a steady state temperature, which it would reach, it would be at the same position at all times. And fill in this V net and see the visibility factor 1 to 2 times the area times the constant times the temperature minus the same but now the other way around. And you can see that those constants going out. Also f to the 1 was 1, so that one's also going out, or it's equal to 1, but it's the same for now. And then you can rewrite this with some mathematics to the 4 root square of the product you see on the screen. And if you fill in the numbers, you can find the answer we were looking for, which is 394 Kelvin. And know that this is actually quite hot, and that space companies will do everything they can to make this temperature go a little bit lower by, for instance, putting some foil on top so it will be more reflective. Because now we've assumed it to be a black body, so it will absorb all the radiation from the sun. But in reality, this will not be the case, since they have made it more reflective. You had to do the same type of exercise, but now for the bottom part of the satellite. So I made a new sketch for this. And note now the bottom part is here at the bottom. And there, so is your temperature 3 and the temperature 4 is of the Earth. And note that also now the Earth is radiating, so this is infrared radiation in the same fashion and was going on the sun, because also the Earth is a sphere. So again, we have this outer mantle, and we have a distance between the Earth and the satellite, which I say is the S between the satellite and the Earth. And also the satellite is radiating back. Again, it was isolated, so nothing is going through. Note that also in this exercise we have shown that this was clearly not the case. In the last exercise you had to prove this, because the conduction was about of equal order of magnitude as the radiation that was sent to the satellite. And now again we have to make a balance over the energy, and I'm going to use a little bit of another trick here, because I'm just going to say that this balance is the radiation. So this is at point 3 at the satellites, the radiation coming in from the Earth minus the radiation sent out by the bottom of the satellite. And why I'm doing this is because the Earth is not a black body radiator, but had a epsilon there. And I can also do this with the F visibility factors and the F net, but this will be a little bit more complicated than the way I'm doing it now. But V4 to 3 will be of equal size, of course, because it's steady state. I'm just saying V3 is losing all this radiation and doesn't really matter where it goes to. That's the only difference with the V net. So again, I have to find a visibility factor, V 4 to 3. And I'm just writing out the energy balance now. So V43 times A4 times a constant times the temperature times the epsilon is equal to what's losing there. And you'll see that this is an easier expression, for I have no visibility factor here. And then this is the result. And I can easily write this to an equation with which we can find the temperature of the satellite by just rewriting the variables into this particular form. And note that the only unknown now still is the visibility factor. And we can calculate it the same way as we have done for the sun and the satellite. So we're taking, in this case, the area of the bottom of the satellite and the E4 star. And this time I'm not going to replace the R star by just the difference between the Earth and the satellite, because the R of the Earth is of the same order of magnitude as the distance between the Earth and the satellite. So I cannot take one out. I just have to add them up. And I have the number, so it's actually no problem. And then I can fill in the whole equation and find the final temperature, which is this cold. And you can see that the difference between the two temperatures is actually quite high. Also, one of the reasons why we cannot neglect conduction in the real situation. Well, thank you for your attention. And if you still have any questions, you can still ask them on the forum. Bye.